Welcome to Frontiers of Research. I'm Antoni, and today we're exploring one of the most fascinating problems in the foundations of mathematics, the Continuum Hypothesis and its remarkable independence results. Joining us again are Dr. Rachel, our expert in mathematical logic, and Josh, who will help us navigate the historical context. The Continuum Hypothesis was first formulated by Georg Cantor in the late 19th century as part of his groundbreaking work on infinite sets. For over half a century, it remained on Hilbert's famous list of unsolved problems, until astonishing developments by Kurt Gödel and Paul Cohen revealed something truly extraordinary about its nature.
Georg Cantor revolutionized mathematics in the 1870s by developing the theory of infinite sets and introducing the concept of different sizes of infinity. He proved that not all infinite sets are created equal. Some are genuinely larger than others. The natural numbers like 1, 2, 3, and so on form what we call a countable infinity, which Cantor denoted as Aleph 0. But he then showed that the set of real numbers, or the continuum, is strictly larger. It's an uncountable infinity. This discovery was earth-shattering for mathematics, opening up a hierarchy of infinities that ascend forever.
So what exactly is the continuum hypothesis, and why did it become such a central problem in mathematics?
The continuum hypothesis asks a seemingly simple question. Is there any set whose size is strictly between the integers and the real numbers? In Cantor's notation, if Aleph 1 is the next infinity after Aleph 0, the hypothesis states that the cardinality of the continuum equals Aleph 1. In other words, there's no intermediate infinity that sits between the countable and the continuum. Cantor himself believed this was true, but despite years of effort, he couldn't prove it. The problem became the first on Hilbert's famous list of 23 problems presented in 1900, showing its central importance to mathematics. For decades, the greatest minds attempted to prove or disprove it, but all attempts failed.
Rachel, could you walk us through how this problem evolved in the early 20th century? I understand there were significant developments in mathematical logic during this period that would eventually prove crucial.
The early 20th century saw a crisis in the foundations of mathematics, partly triggered by paradoxes discovered in Cantor's set theory. Mathematicians like Zermelo, Frankel, and Russell developed axiomatic systems to place set theory on a rigorous foundation. Meanwhile, the formalist program, led by Hilbert, aimed to prove the consistency of mathematics. But then came a seismic shock. In 1931, Kurt Gödel published his incompleteness theorems, showing that any consistent formal system containing basic arithmetic must contain statements that can neither be proved nor disproved within that system. This revolutionary result suggested that certain mathematical questions might be undecidable, something previously unthinkable.
How did Gödel's work specifically relate to the continuum hypothesis?
In 1938, Gödel made a breakthrough by proving that the continuum hypothesis cannot be disproved using the standard axioms of set theory, known as ZFC, Zermelo-Frankel, with the axiom of choice. He did this by constructing what's called the constructible universe, a model of set theory where the continuum hypothesis is true. This was a partial resolution, showing that if ZFC is consistent, then so is ZFC plus the continuum hypothesis. But the other direction remained open. Could the continuum hypothesis be proved from ZFC? This question would remain unanswered for another quarter century.
This brings us to Paul Cohen and his groundbreaking work in the 1960s. Rachel, could you explain how Cohen completed this remarkable story?
Paul Cohen developed an entirely new mathematical technique called forcing to tackle this problem. In 1963, he used this method to prove that the continuum hypothesis cannot be proved from the axioms of ZFC either. Combined with Gödel's earlier result, this established that the continuum hypothesis is independent of the standard axioms of set theory. It can neither be proved nor disproved. Cohen's achievement was immediately recognized as revolutionary, earning him the Fields Medal in 1966. Forcing has since become a fundamental technique in set theory, used to establish the independence of many other mathematical statements.
Could you explain more about this forcing technique? It sounds fascinating. Why is it called forcing, and how exactly does it work?
The name forcing comes from the key idea of the technique. We literally force certain statements to be true in an extended model of set theory. Cohen started with a model where ZFC holds, then systematically added new sets to create a larger model where ZFC still holds, but where the continuum hypothesis is false. The term forcing refers to how these new sets constrain or force the truth values of statements in the extended model. It's somewhat like building a complicated mathematical structure, piece by piece, where each new piece must be compatible with all previous pieces and forces certain relationships to hold in the final structure. What's remarkable is that Cohen showed this extension can be done in a controlled way that preserves the truth of all ZFC axioms while changing the truth value of CH.
How has forcing been applied beyond Cohen's original work on the continuum hypothesis?
Forcing has become one of the most powerful tools in modern set theory and has been refined and extended in numerous ways. Iterated forcing, developed by Solovay and Tenenbaum, allowed mathematicians to handle more complex independence results. Martin's axiom, a principle that can be forced to be true, has applications across mathematics. Sahar and Sheila used forcing to prove the independence of countless statements in infinite combinatorics. In 1984, Sheila showed that the Whitehead problem in group theory is independent of ZFC, the first major independence result outside set theory. Wooden's work on large cardinals and determinacy uses sophisticated forcing arguments, and Todorcevich applied forcing to problems in topology and functional analysis. Forcing even has connections to theoretical computer science through the study of generic computability and randomness.
This seems to have profound philosophical implications. Does this mean the continuum hypothesis has no definite truth value? How do mathematicians interpret this independence result?
That's a profound question that goes to the heart of the philosophy of mathematics. There are multiple perspectives. Some mathematicians, known as Platonists, believe there is a single mathematical reality where the continuum hypothesis is either true or false, and we simply need stronger axioms to determine which. Others take a more formalist view, seeing mathematics as a formal game where different axiom systems give different valid mathematics. In some extended systems, the continuum hypothesis is true, while in others, it's false. There's also a multiverse view championed by Hugh Wooden and others, suggesting that there isn't just one set theoretic universe, but many, with different properties. The independence of the continuum hypothesis has become a prime example of how mathematics isn't simply about calculation, but involves deep philosophical questions about the nature of mathematical truth and existence.
I understand that mathematicians have proposed various additional axioms to resolve the continuum hypothesis. Could you tell us about some of these approaches?
Many set theorists have proposed axioms that extend ZFC and would settle the continuum hypothesis. Large cardinal axioms posit the existence of extremely large, infinite sets with special properties, creating a richer hierarchy of infinities. Forcing axioms like Martin's maximum suggest axioms that restrict the kinds of sets that can be constructed. Wooden's ultimate L is another approach. Interestingly, most of these natural extensions actually suggest that the continuum hypothesis is false, contradicting Cantor's intuition. But there's still no consensus on which, if any, of these axioms should be adopted. The study of these axiom systems has developed into a rich field called set theoretic geology that explores relationships between different models of set theory.
Beyond pure set theory, has the independence of the continuum hypothesis and the methods developed to prove it had impacts on other areas of mathematics?
Absolutely. The independence phenomenon extends far beyond the continuum hypothesis. Paul Cohen's forcing technique has been used to establish independence results in many fields, including topology, functional analysis, and algebra. For example, Saharon Sheila has shown numerous independence results in infinite combinatorics. The Whitehead problem in group theory was shown to be independent of ZFC by Sahara and Sheila. Independence results have also appeared in measure theory and functional analysis. Perhaps most profoundly, these developments changed how mathematicians think about their subject, highlighting the role of axioms and showing that even seemingly concrete mathematical questions may not have a single, definitive answer within our standard framework.
Thank you, Rachel and Josh, for guiding us through this fascinating journey into the independence of the continuum hypothesis. From Cantor's initial question about the hierarchy of infinities to Gödel and Cohen's revolutionary demonstrations of independence, we've explored how a single mathematical problem led to profound insights about the nature of mathematical truth itself. The story reminds us that sometimes in mathematics, the greatest discoveries aren't definitive answers, but deeper understandings of why certain questions resist our attempts to resolve them. Join us next time for more explorations at the frontiers of mathematical discovery.